All right, let's dive into one of the biggest, most fundamental challenges in all of AI, representation learning. This is all about teaching machines to actually understand data, not just, crunch the numbers. But why is getting this right so incredibly hard?
So yeah, what makes this so difficult? I mean, we've got mountains of data, right? So why can't a machine just sort it all out? Well, that's the big question we're going to unpack today. And here's how we're going to tackle it. We'll look at 4 key hurdles. First, a core trade-off that's right at the heart of the whole thing, then the classic problem of overfitting. After that, a really weird puzzle about something called pre-training, and finally, we'll talk about the infamous curse of dimensionality. Okay, let's get into it. So, first up is the most fundamental challenge of them all. You gotta understand that representation learning is, at its core, a constant balancing act. It's this non-stop push and pull between 2 goals that are always competing with each other.
And this really shows you that core tension. See, on one hand, you want to keep every single bit of the raw, messy information from your original data. But on the other hand, you want a representation that's clean, simple, and easy to work with, where all the features are nice and independent. Think about it, like trying to summarize a book. You can't possibly keep every single word to preserve all the info, and also have a neat one-sentence summary. It's always a compromise.
All right, let's move on to our second challenge. Now, this is a problem that anyone who's dabbled in machine learning will definitely recognize, but it has a special twist here. I'm talking about overfitting, which is basically what happens when a model learns its job a little too well. So when a model trains on data that's perfectly labeled, it can get, obsessed with the tiny details of that specific data set. It starts learning all the noise, all the random quirks, and it gets so specialized that when you show it new data, it just completely fails. It's like you memorize the answers for one specific test, but you're totally lost when you have to solve any other problem. You know, that whole overfitting thing leads us straight into our third and honestly maybe the most fascinating challenge. If supervised learning can backfire, maybe the answer is to let the model learn on its own first, with a bunch of unlabeled data. This is what we call unsupervised pre-training, but its real role is a total puzzle.
So the idea behind unsupervised pre-training, or UP, is actually pretty simple. Before you give the model a specific test with all the answers labeled, you first just let it read the library. You feed it a huge amount of unlabeled data. This way, it learns the general structure and context of the information and builds a really strong foundation. This whole process acts as what's called a regularizer, which is just a fancy way of saying it's a technique that helps prevent the model from overfitting later on.
But here's the catch. Unlike a lot of other areas of machine learning, there's no single, clean math formula that says, this is how you do it. There's no universal recipe for success, and that makes figuring out how and when to use it incredibly tricky. And that leads to a discovery that is, frankly, shocking. When researchers looked at its effect across tons of different tasks, what they found was that, on average, pre-training was actually slightly detrimental. It made things just a little bit worse.
And yet, and this is the puzzle, right? In certain cases, it can be a massive, game-changing help. Sometimes it's the one thing that makes a model work at all. So how can the same technique be kind of unhelpful on average, but absolutely essential in just the right situation?
And this image just illustrates the effect perfectly. Take a look. You can see how data points get organized by 2 different models. Those scattered blue circles, that's a model without pre-training. But look at the tightly clustered black triangles. That's a model with pre-training. You can literally see how dramatically pre-training can change the whole representation the model learns, creating a way more organized structure.
So here's how we solve the puzzle. It turns out pre-training is most helpful when your starting point, your initial representation, is really weak. Think about language processing. A very basic representation called a one-hot vector just tells you what a word is, but gives you 0 clue about its meaning. Pre-training is what builds that crucial context. But for lots of other problems, you're just better off with standard methods combined with good anti-overfitting tricks like dropout. It really all comes down to how good your model's starting point is.
And that brings us to our final challenge for today. It's a classic concept in machine learning that's a real headache for simpler models: the curse of dimensionality.
So what is this curse? Well, imagine you keep adding more features to your data. Things like height, weight, age, location, and so on. Every new feature is another dimension. And the more dimensions you add, the space your data lives in gets exponentially bigger and, emptier. Your data points get spread so far apart that trying to find a pattern is like trying to find a few people scattered across a massive desert.
Now, this curse is especially tough on what we call non-distributed or symbolic algorithms. We're talking about things like k-means clustering or decision trees. These are models that basically work by creating a separate rule or parameter for every single category or region they find in the data.
And that's the real problem, see? For these models to understand a new category, they have to have seen an example of it first. They just can't generalize to new combinations of features on their own. What this means is that the amount of training data you need just explodes exponentially as you add more dimensions, and that becomes impossible fast. But, and this is so cool, this is where deep neural networks come in with a brilliant solution. They use something called distributed representations. Instead of learning one rigid rule per category, they learn broader features that can be mixed and matched in new ways. This lets them understand a mind-boggling exponential number of possibilities using a way smaller, more manageable number of parameters. It's a huge leap in efficiency that lets them generalize way beyond what they've been explicitly taught.
But just to bring it all full circle, even this incredibly elegant solution has its own trade-off. The model gets all this amazing power, but it comes with a catch. You can't just use any possible combination of features, and you can't learn just any old function you want. The very structure that gives it power also imposes its own constraints, which brings us right back to that fundamental balancing act we started with. So let's just recap. At the end of the day, the challenges of representation learning are all about navigating these really complex trade-offs. It's that constant balance between preserving information versus getting useful properties. It's managing the power of supervised learning while dodging the bullet of overfitting. It's figuring out that weird, ambiguous role of pre-training. And it's overcoming the curse of dimensionality to get to real generalization.
And that leaves us with one last, really crucial question. We're pretty sure a single perfect representation is impossible. Every single approach we have involves some kind of compromise. So the real challenge for the future of AI probably isn't about finding some magic silver bullet. It's about learning how to choose the right set of compromises for every unique problem we want to solve.